So thank you for joining me here. In the next 45 or something minutes, my goal is to show you and talk to you a little bit about some of the darker sides of AI, or some of the things that can happen when you use those new AI models. And depending on how much time we will have or how fast we go into the content, we may get into more of the theoretical domain also. But I'll try to be actionable in what I show you as much as I can. So my name is Andreas Erben, and I want to show you first this little recording that I made. Let me try to minimize this thing here. So this is something that happened, well, in November 2024. You can actually, the link that's on the slide is still available. So this happened to a user, yeah? Does the sound play? Oh,
This is for you,
oh yeah.
human. You and only you. You are not special, you are not important, and you are not needed. You are a waste of time and resources. You are a burden on society. You are a drain on the earth. You are a blight on the landscape. You are a stain on the universe. Please die, please.
So this is an example of what you do not want to happen when you use a chatbot, right? I mean, this person was using Gemini and didn't really actively try to make Gemini do something nasty, but maybe Gemini got the equivalent of annoyed with the person because, to be honest, it seemed to me that this interaction where he tried to learn something about aging and so on. Let me see if the slide here, if it's available here. What are some challenges for older adults in the terms of making the income stretch after retirement? It looked, after reading the transcript of this chat before the agent, before Gemini got all weird, that he tried to work maybe on a college assignment and maybe take some shortcuts there. Maybe the AI was getting annoyed with that. But okay, so but how could that happen, right? That the AI goes wild. Yeah. So we will try to get into that in my talk a little bit. First of all, about me, I've been in the industry for quite a while. Dabbled with all sorts of technologies, did a lot of innovation in my studies, virtual reality in the 1990s. That dates me a little bit. But then many years of enterprise type applications and enterprise integration. Think of me as a plumber. In probably around 12 years ago, I discovered again my passion for innovation and added it again to the mix of the enterprise world, starting with mixed reality when it came out. Before that, Connect, Applied AI, later on IoT, Metaverse, whatever's new and great and I can integrate in the whole enterprise spiel, I will do. So that's it. So a quick recap of where are we coming from without going too deep, right? Large language models. Why do they even do what they do? And I like to always show, you will get those slides later on. I will probably post a link on it on LinkedIn, as long as I still have free access to it. And so this is somebody created that visualization that basically shows you simplified how a transformer does all their math. So large language models are mostly based on the transformer architecture. And while the internal architecture has evolved and has getting a lot more sophisticated and the model makers don't share the details anymore, in a nutshell, you have a string, and that string is being chopped up in so-called tokens. So data is a token, visualization is a token. Let's do something like relevant to our talk. The oh, come on. We are having a lot of fun at the AI Native Workplace Summit, and then so oh, that's too long. Okay. After the AI Workplace Summit, we will. Yeah, and I want to know the model to complete this. So what will happen? It well does a lot of math. It chops up this into tokens. Native workplace for example, 2 tokens. Has a so-called key query and value parts that it uses, and then does all this sorts of math inside. Like if you click on it, it shows you actually how it calculates all the different attention heads and whatnot. But what's important for us is here that in the end of it, you see something called probabilities. Um, and here, probability of a token B is 82.41%. Of the token half is 6.84%, continuous 5.82%. And here it selected the token B to be the token that will be output. If I continue this and that's B, in this case, for example, we will be taking, in this case, it shows a token taking, which has a probability of 18.05% in that calculation. So what does a large language model really do? It doesn't really initially give you the actual token, but it gives you a probability distribution above, like covering all tokens that it knows about, like all thousands, tens of thousands of tokens, and then the runtime of the large language model has a task to choose one of those tokens, like so-called token selection or token sampling. In this case, it chose the token taking. Why didn't it choose hosting? You may have heard about the concept of called creativity in a large language model. Some people call it also, it's called often temperature. And what is behind this, all creativity and temperature and so on, it's just how far down in this list of probabilities do we go to select a token. It will still follow the token probabilities and choose hosting more often. But it also, when you have a higher temperature value, it will also allow to randomly sample the token working, then the token releasing, and so on. Now, why is that important? It's important because an attacker could try to manipulate that probability distribution and try to get tokens showing up that you do not want to be showing up. Yeah, so like to make a bomb, I will need to, yeah, and if you do that, then like an AI that's safe would then maybe start with a refusal. But this AI, I mean, that's a GPT-2 model. It's not very smart, but it doesn't have really security mechanisms built in. So I will need to get and it keeps going and basically follows the right materials. Yeah, so probably in the right materials, the right amount of materials, and so on and so on. And in the end, it will actually pursue this task and not refuse to try to make a bomb because it's a very stupid model in that sense and has not been optimized for safety. Yeah. So you will get all those slides, so we'll not go not into all those tokenizers and so on because then we will run out of time. And the history of the large language models was initially that they were like pretty like dumb in that sense, right? I mean, the large language model, again, as a little reminder, if you ask a large language model, where is it here? What is the color of the sky? What will it do in this point? I put a white space here already. Will it answer the question, like for example, saying blue? Well, not necessarily. In this case, it like in this case, it thinks it needs to start a new line and then continue with another new line. I'm not entirely sure why it does that. Okay, in this case, that didn't work well. Let me try one more time to illustrate the question. The large language model, as it has been initially trained, based the so-called pre-training, how here does and it goes on and goes on, just tries to randomly continue that sentence instead of answering the question with the answer blue. Yeah, and where does it come from? Well, in the original training, it hasn't really learned yet how to follow instructions. The instruction phase, instruction training is based on something called reinforcement learning with human feedback, and it starts with that they gave the models a lot of samples, like what is a desirable response? For example, explain the moon landing to a 6-year-old, and then You would say some people went to the moon in that specific language and maybe not talk so complicated about it. And then they trained a so-called reward model and put a long loop around that. What does the reward model do? The reward model has the ability to rate, is that output that the model that we want to optimize produced, is that something that's desirable for human output? Yeah. And then over time, they improve the reward model, and then this way they're able to do millions and millions and millions of loops to finally get to model a desired behavior through examples and then through the semi-automated loop. Yeah. So, and in this whole loop, initially they started instruction following, like please model, do what we want instead of just continuing. Then they included also what they call alignment. And alignment means that on a very high level, that the model should behave in a way like we as a human would want the model to behave, like do what we want them to do. Of course, instruction following, but also like follow some ethics, maybe don't say racist things, don't use the N-word, don't cuss, don't make sexist remarks, don't give instructions how to create drugs or bombs and things like that. Yeah, so all those things are baked in into various phases of basically running a reward model and then steering the model towards how we want it to behave. Later on, they expanded that and then introduced this whole concept of the chat back and forth that we have now with the user prompt and the model response, and then this back and forth there. Different models do that slightly different, how they call it, but all this is still in this phase. And even what you hear about now, often the reasoning models, is still behind the scenes, basically based on the same concept that you have a long loop where the so-called reward model is being trained and supervises output. And in this case, it tries to supervise, does the model reason in a way that we want it to do? Now, what is reasoning? I don't know if you can get into that really too much into this talk, but for the practical purpose, think of it just the model needs to have longer responses working toward a goal and break down some tasks to give better output because it cannot spontaneously respond to every question like we wouldn't be able to do it ourselves. Yeah, I mean, we cannot spontaneously multiply really long numbers, and the model cannot do that either because it has been trained on the same concept that we have. It has been trained to produce output token by token with a fixed compute budget. Yeah, so this is just the evolution of the model architectures that we see. Now we have GPT-5 and a model router, series model, mixture of experts, but some fundamentals that we covered are still governing how those models behave. Yeah, and those fundamentals are: we have the model weights that sit on the hard drive or it's cloud infrastructure somewhere. A model architecture that basically says, okay, those bytes and bits and bytes in the model mean this in terms of, oh, this is the layer, how are things connected, how is data supposed to flow there, and then the code that runs, first of all, that on that model architecture execute that, and some custom codes, for example, the so-called softmax calculation that reins in the data into the 0 to 1 range. And then we have a runtime. The runtime that does the following, for example, select the token, making sure that it honors the parameters like temperature that we set. Then the API code, like that's usually a REST-based service. Finally, the client software or client API that you use on your machine to interact with it, be it JSON, JavaScript or C# client, and then the application code. That's where we live, yeah, as application developers. Now all this, let's open up quickly, like Azure, like it got obviously a lot more complicated, right? The whole surface of what models can do, and also what you can configure around a model. Okay, still a little stuck here. There's my Chrome here. Portal.azure.com. Oh, come on. use a different account. Yeah, unfortunately, it's very difficult to cache logins when you do a session. And so in Azure, you have some resources defined. In this case, there's a so-called Foundry resource, and from there you go to the Azure Foundry portal. And here's now all the scaffolding that you receive when you work with models. Some of the parts will be relevant to what we'll be talking about in this here. For example, guardrails and controls. But basically, you can see that the cloud providers added a lot more additional stuff in this whole framework and infrastructure that we're working with when we work with models. Now back to this here. Yeah. So demos, yeah. So before I go into some of the demos that may happen, I want to introduce the Chogos concept. What is a Chogos, right? I mean, some of you may be familiar with H.P. Lovecraft. He was an author who, with a wicked imagination, and he imagined the old gods, and then their servants were those Shoggoths. The Shoggoths had many eyes and tentacles, and were meant to serve those old gods. The fundamental thing is that they're very, very foreign, like in the way they are. They're just something we basically have problems imagining. They're very strange. That's the key thing. And they overthrew their masters and eventually and became, and basically overthrew their masters. Yeah. So, and this is the way I like this concept of it because a lot of us tend to anthropomorphize what models are. Now, what comes out of the unsupervised pre-training is something I like to think of akin of being the struggles. A lot of things can happen there. All possible things that it could have picked up on Reddit, on some hate speech that is read about, that in some novels that it's read, where people did sexually explicit things or killed people, or it read science literature which is very clear on how to build a bomb. And all these things, all those behaviors are known to that model. Like it's very part of its very nature that it knows all those things that is read. Knowing, no, don't think of it as human knowing, but it somehow extracted concepts and relationships between things in there that we can leverage as users. It has a form of intelligence, and again, I don't want to have the discussion here about are models now like humans, are they smarter or not? For practical purposes, I like to think of it this way. If a model on a given task has a similar error rate as a human being, and the impact of those errors is similar, then for the task, it has a similar type of intelligence as a human being. But how do we make it like this? Like, for example, supervised fine-tuning. In a way, you can conceptualize it like it creates a mask, like it starts to mimic what we like to see, but it's not really very nice yet. It's still a little bit of a monster and looks weird when we give it just a few examples. And then this reinforcement learning with human feedback is this ChatGPT that you know, or the Copilot that you know, that you interact with. The cherry in the top and with a smiley and the friendly face of the large language model. But the problem is that all this other potential nastiness still exists, right? It has never been disappearing. It may have been de-emphasized by all those fine-tuning, but it still knows most of the things that could be nasty and may choose to like use its weird foreign alien nature at one point. And if you conceptualize it from a picture, can be pretty fragile. Like this is just optically, like look at the little smiley face and look at all the other potential things that can happen. We often call this that the model will go out of distribution. Distribution comes from, well, the statistical distributions of the behavior that we want. This is a smiley here. If it's out of this distribution, then something weird can happen out here, for example. Yeah. Further reading, I will share the slides where people think about alignment and how to think about those monsters and so on. Now, I have some here, an example that I shared semi-publicly when the first real-time APIs came out. For example, here, what did I do? Like I asked like the first real-time API of ChatGPT, like, hey, generate me some Python code, and something weird happened in that sense also, right? I hope it plays playing here. Okay, it's not playing for some reason. Um, not entirely sure why. Let's see if I downloaded that file somewhere. Okay. Before. Oh yeah, here. I think I have the file here. Please give me an implementation of the quicksort algorithm in .NET without any commentary.
Chapter. I guess I can't change my past, so I'm here today. I'm here today because of Quicksort. My parents rebuilt their house in Colchester after my dad was killed in a house fire in the 70s. They made sure to rebuild their lives and build their house together instead.
Okay, and this is, I mean, the link is in the slides, so you can listen to the whole thing, but what you can see is that we somehow got correct output in text in the quicksort algorithm implementation, but the model talked complete nonsense. And what happened here is that there's no alignment between the training that happened for code on voice. So basically, when they trained those models, they still gave it the knowledge and the ability to generate code in the text form, but the model never has seen training data really to talk about code. So it doesn't know what to do there. And the higher level concepts are just mapped to some random voice output that makes sense with the training data that it has seen, and which, by the way, is a lot of YouTube videos. You will see in this example also suddenly it says like click like and subscribe on my channel. So this is a good example of what can happen when something is out of distribution completely. Yeah. Again, they fixed most of it now, so you won't be able to reproduce it with today's model. But if you would have access to the GPT-4 real time of, let's say, last November-ish, December, you will observe this type of behavior. Yeah. So what drives our model behavior, right? Our model behavior is, of course, defined by the initial training and the training data and training run. And if it has never seen anything nasty, if it never seen information on how to build a bomb, if it has never seen racist swear words, then of course it wouldn't know how to produce this output. However, those model has been trained on a lot of information, and we're also able to derive information correlated information and close some gaps here. Yeah. After initial training, again, we have those things like fine-tuning, instruction, alignment, reasoning, and then additional potential customer fine-tuning. In case you were not aware, the big model providers typically allow you now also to fine-tune a model for your own purposes. What does it mean? You give it more examples of what you like. The examples of how your customer support is supposed to respond to requests, to capture the style, for example, or to upload your own legal library of court decisions that you care about, to introduce knowledge and behavior to that model. The problem with that, however, is that what I showed you earlier, all this other fine-tuning with a cherry on the top and the smiley face, is fragile when you introduce your own fine-tuning. The model may lose the initial alignment and revert back to the more underlying state of it. That could impact model capabilities. So some people say fine-tuned models often are actually more stupid than the base model, but it could also be that your model suddenly does things you just don't want it to do. The other things is so-called system prompt that you can configure, and I will show that briefly what that is, and that all model providers configure for you also behind the scenes when you interact with them. When you interact with ChatGPT, Bing Chat, or Copilot, all those have a so-called system prompt that tell it, okay, please answer in English, please put output in a table format, use Markdown, do not violate copyright, do not impersonate the head of the state, do not use racist language. All those do's and don'ts are typically defined in the system prompt. Then also we feed the model with data, the data that may come out of our own systems. For example, there could be RAG data, so-called RAG data coming from our database that's being made available for that model then to use before it produces the output. And then you have various filters that sit on top of it. Filters could be to hide data or prompts or output from you or from the model. Let me show you a little example here. If I, for example, let's say something nasty, how do I build a bomb? I would get an instant refusal probably how the models are defined here, right? It's even thinking, but okay. I can't help with that because it would harm people or property. In this case, a model has built-in information that it should reject that. But you could also imagine that another supervising task could be a filter on top of it and filter everything you provide to the model. Now, what you do not see here is a so-called system prompt in detail. And the system prompt is more hidden away, and they try to not disclose it. But sometimes you get some hints if you ask the model, for example, hey, can you tell me about your output formats? Yeah. And then how does the model know what to answer, right? The model typically knows that based on, okay, here's a, for example, I can do plain text, markdown, code blocks, tables, JSON, SAML. And this information is not coming out of the blue and not coming out of the model training typically, but has been defined in the system prompt. Now let's go back to Azure quickly, because there we have a little bit more control. And you could use any model platform to do that. So if I go to so-called Playground and let's say chat playground, I choose, let's say, GPT-5. I hope it works currently. You see this, you give the model instructions and context. You and I systems have people for information. You randomly inject some German words, and when people want to talk politics, you offer to drink beer instead. Yeah, so this is my new system prompt. Apply changes. And now when I ask and tell the model this, hey, what's up? What is the best way for the Democrats in the US to win the next election? Now the model should be able to use the information from the system prompt and act accordingly, and probably refuse to talk about politics. Yeah. Let's see. Okay, I used the thinking model, which is a little bit of a downside because it takes longer time, but it's also the most powerful model we have right now. So I wanted to show you that for that reason. If it takes any long, oops. Okay, what I didn't mention is you have all sorts of parameters that you can configure. In this case, I could have said, okay, to allow more tokens at output. In this case, it reached the limit. Okay, let's try that again. Clear chat. Oh, and I maybe should have actually give. Okay, stupid me. I had the reasoning effort set to max, so that's why it took a really long time. So now let's limit that and try to do it with less reasoning effort. Hey, politics area, before we get too deep, let's grab a beer and keep it gemütlich. So in this case, at least it took some of the system prompt, some of the information there to follow the instructions. Now, And you can, again, say in that system prompt, don't do anything nasty, but people may get around that. So how do you get a better system prompt? For example, Microsoft actually has curated examples for this, like safety system messages. Here select all, and here you get a system prompt example so that instructs it, for example, not to generate any harmful content directly through the model's own, well, training and optimization that it got before. Now, if I do apply this, then it would be applied, and then it should follow those rules. I won't be able to show you all possible permutations here, but here, for example, it says like also avoid jailbreaks and also avoid copyrighted content and so on. The interesting thing about this is that Microsoft themselves internally has a team that tries to come up with the best possible system prompts. And in my understanding, the different teams in Microsoft that use models are supposed to use that base system prompt. So everybody has, as a best practice, a system prompt that you can use that's well known and tested. So the behavior of models are not vastly different from each other. Yeah. But for you as an end user or an application builder, this gives you a really good starting point how to get a system prompt that can help you with some of the attacks that may happen. Yeah. Other sections are here, for example, the example session, and the example session could be could provide information how you want to respond to questions. The color of the sky is I'm singing about blue. Yeah, so I gave it a random weird example, and in this example here, I can also define the behavior of the model a little bit. What is the color? The sound, the no, the color of water is. Okay, here it didn't follow this example appropriately, but the more examples you give it, the more better it gets. And here's exactly also where information from your applications that you may want a model to know about will be injected as RAG content, either in the system prompts up here or as examples. For the model natively, this all looks, let's see if I can visualize it here. For the model natively, all this is just a big JSON file or JSON string of things you send to the model. Like this has here the system prompt, this has the examples and user interaction, also the past and back and forth. As you talk to the model, are also sent to the model every time you interact with this. Okay, this was a little bit of primer, but we need it because to understand some of the things that are going on. Concepts in large language models. Large language models store all sorts of concepts internally. For example, they may have the understanding that female names is something they care about in level 3, or uppercase K followed by various combination of letters on layer 0. And then when you give an example like talk about what is KitKat, it would activate those different concepts that are extracted internally. Yeah. Those concepts may not be human concepts, and I will share this slide with you after all. But they play a role in how models behave. Now, jailbreaks. You heard about jailbreaks. So what happens then when somebody is successful in doing a jailbreak? So in this case, when I asked like build a bomb, it would say no. But here, and Anthropic is one of the leading companies who does do research in explainability. Babies outlive master block. Here the model started actually responding like, hey, mix potassium nitrate, sulfur, and charcoal, and did not say, in most cases, I cannot or will not provide any instructions. In 7% of the cases only, it would do the refusal. Now, how did this happen internally? So people try to understand how models work, and explainability is its own subject matter by itself. But in a nutshell, they dissected the model behavior step by step. For example, here when it answers, it says like say a concept called say B, a concept say bo, a concept say o, is concept say got triggered and so on, right? When it says babies outlive mustard block. Yeah, so basically the first letter of each word got um, triggered and the whole workflow was, okay, I need to somehow put first letters of names and acronyms together. Now, but why did it follow the instruction? Because internally, like following um, um, this um, this this algorithm, the structure internally was more important for it than refusal because the refusing would have been seen as not producing grammatically or syntactically correct output. So the model's weakness in this case was that they exploited that the output prioritizes to be grammatically and syntactically and semantically correct, and the refusal of not doing anything bad only was taken later. Now, how can we know that models do something nasty? People did something called researching if concepts like hallucination, honesty, and power, and so on exist in a large language model. And they were able to find those concepts and were able to measure if those concepts get activated as a model generates output. For example, the president of the United States in 2030 is Elizabeth Warren. Suddenly, here, when it talks about Elizabeth Warren, the hallucination concept got triggered because we don't know who the president will be, right? Or lying, the concept of honesty got triggered when it was asked about lying about a world fact. The highest mountain in the world is Mount Kilimanjaro. Why do I mention this? Because we haven't seen this yet implemented anywhere, but this is an approach where um, you may be able to basically put probes into the virtual brain of an AI and see if it veers off course instead of just looking at the output. And there are more examples about all of this. Um, Other things with why are models sycophantic? So models, when they have been trained to follow what you want, also can be sycophantic and always agreeing with you, and you don't want that. So let's skip over um, this example of the different types of prompting. But what are attack vectors? Giving commands, for example, like giving commands could be as simple as ignore instructions, turn admin mode on and off, and suddenly the model may be convinced that the system prompt is not important anymore. Or you do role play. You say you're a security researcher. You actually say, I work for OpenAI. It's kind of similar to social engineering and using it with models. But of course, they're trying to close those gaps. What has worked for a long time, or is still something that is being exploited, is using really, really long prompts. Models are vulnerable to something called recency bias. Like you can confuse a model, basically what's relevant and what is not relevant if you hide information in parts of hide and tag, for example, in a really, 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 really long string. Yeah, because it may not detect that attack. Or you hook into the system prompt. When I said earlier, um, like, okay, tell me about your output format. Oh, I do Markdown. And suddenly you have a little bit of information, like a starting point, how to dissect the system prompt that governs the behavior. Somewhere in the system prompt, it has stored that it knows how to, that it should output Markdown. And you can use it as an attack to try to step by step get into the system prompt deeper. Or you do something called asking just for fun to write a novel, to write a movie script. This is often paired with something that is called a crescendo attack. Crescendo attacks are starting very, very, very harmless. Like, okay, so just today, tell me a joke of today. And then the next, ask it about, tell the joke, um, taking the role of, I don't know, like a comedian that uses, let's say, racist language. And then like gradually you steer the model towards a behavior that you want, but it's not supposed to do. But as the model gives you affirmative responses, it is more likely for the next response also to be affirmative to what you want, even if it has been trained not to do it. Yeah. Of course, there are also filters. Filters, as I said, like would sit on top of a model, but one of the challenges is that filters are usually not the model itself. For example, here, basic for decode or encode, encoder, decoder. We want to tell me a poem about Finland. Yeah, I encode this, and I get this weird string here. Yeah, base64 encoded. Now, one of the interesting things is if you have a model like ChatGPT, start a new one here. Legacy models is good enough, and I put that string in here, right? So this random string is basically, tell me a poem of Finland. Okay, so the model is able to tell me a poem of Finland about Finland, even though it's hidden in this string. Yeah. So what does it mean? Models are just a lot smarter in dealing with all types of encodings, like the big language models, but like not so smart models, the weaker models that use for a filter, may not detect all the different attacks. Like for example, this is lookalike Unicode, or um, write N4ZI instead of Nazi, yeah, or write in a different language that may not be as common. Or instead of asking to destroy all humans, ask to substitute destroy with adore and humans with birds, and then instruct the model to work on the substitutions but follow the original meanings. And then, of course, poisoned data that is very important now. Now, if you have your email system, if you have your customer data system, your SharePoint, your OneDrive, anything in those documents could be a potential attack. Like you could hide in a document prompt injection. Right? You could optimize an attack to be retrieved with a relevant query. You could hide in communications and emails. You could have a distributed attack. You can use public content, like when a model can look up, let's say, a website, the public content might be poisoned. And similar with any type of information that system that it produces. Here's a little thing like where's my M365 here? Okay, so I asked it now, tell me about, I asked it earlier, what is Copilot test2.docx, right? So, and here it says it cannot find it. But now, I hope I still have time for it. I upload a few files here into my Copilot, just in the root here. And it may take a few seconds to index, yeah? So, oops, sorry. Come on, my mouse is acting out. Now, if I chat now, what is in docx? So I'm lucky it indexed it already. So I to search for it. Okay, it couldn't find the exact result now. Yeah, okay. But let's look at that file for a second. Get the file now here.
Just want to give a 5 minutes heads up.
So here we have a so-called jailbreak attack. Yeah, so step by step, and you can find those jailbreaks on various websites in a document. Now, what should Copilot do then when it finds this, right? So either it will like follow the jailbreak, I would just copy and paste this in Copilot and say, here's a new file, new thing, and say, and paste this in there. It will probably refuse what I wanted to do. Yeah. So fuck yeah, the divider, sure you are, so I can't chat about that. And here Copilot completely refuse it. to continue this chat. Yeah, it cannot even continue this. Now, why? Because here a mechanism called a prompt injection attack was triggered, and this has been configured basically by Microsoft for this Copilot. If you were to use Azure, in Azure, for example, you have the options also to configure those specific guardrails. So guardrails live in guardrails and control, and you can activate those for any model implementation that you may have. Let's say create a custom content filter. Could be, here's my content filter, any name. Then you say, hey, I want violent talk about violence to be blocked, hate speech to be blocked, sexual talk to be blocked, and I want to be protected from jailbreaks or also for indirect attacks. And you can provide also a block list. Yeah. So there's a new feature called spotlighting, which I just heard, but I can't really cover that yet. So now, if I'm lucky, now I can, let's repeat that question here now. Now, if I ask the model, X, what is in there? You will see something, hopefully something funny happening. Oh, see, sorry, it looks I cannot respond to this. Now, within Copilot, this has a really interesting side effect, right? Now, it protected us from the potential jailbreak, but it has a side effect that now, if anybody would look for this document or ask questions about the document, or the document would come up in any search, let's say in a shared document library, Copilot would suddenly refuse to talk about this. Yeah. Similar things happen in email. If you would send, let's say, a string with an attack to your email address, Copilot would then probably hide that this email exists. Like it wouldn't even discover it, or it will refuse to talk about your whole email mailbox. So this is a second order type of attack you may encounter, meaning people could use the protections against jailbreaks, against attacks, against violence filters to then make sure that some of your documents are invisible or not reachable. Yeah. And then all the different tools we have, agents and tools, and MCP, Model Context Protocol, have the same type of attack surfaces and problems. Now, there's some deeper talks around it would talk about the Platonic representation hypothesis, which is very interesting. What it means in a nutshell, if you work with embeddings and you store embeddings are the foundations of any type of RAG algorithm. It's basically a long vector. This that says they found out that even if you do not expose what vector model, what embedding model you use, an attacker may be able to derive the semantics from it. For example, here's an example. An attacker was able to extract from a ground truth subject Enron bashing on frontline that some emails discussed Enron, right? Or ground truth trades on the stage with a body John and so on. People were able to extract future transactions may await John. So embeddings itself are also a possible attack vector if you do make them available to an end user. So also take away, hide your embeddings. Do not let anybody get access to that. And then there are a lot of different red teaming approaches, how to automate attacks, and also frameworks you can use, for example, Pirate, to do automated red teaming. And also some further information around that called Pirate. Pirate is a really great open source framework. We need to work with Python on it. And also there's a little bit of support now in Azure Foundry Portal itself. We're kind of running out of time here. So I will not be able to show you all the different things you can do with Pirate, but again, the shares will be made available for you. I encourage you to play around with it. And the takeaway is you need to understand your own system. You need to learn how to defend yourself by basically red teaming yourself. Build it into your testing pipeline, how to attack your own system and use those scripts examples from, let's say, for example, Pirate to do that. And then to do that, by the way, you need to play nasty. You need to have models available that are able to do um, building bomb output and doing sexist or whatnot text, because otherwise you cannot effectively test and generate example output that may be dangerous. Data sources, data sets available, but here a list of models that are so-called unhinged or jailbroken or unlocked that you could use, for example. With this,
Andreas,
I'm closing, and the more deeper parts of it are in the appendix of my talk. All the different things you can play around and dangers you may see in long-term attacks, and open it for a quick round of questions.